Hi everyone. One of the things that we're going to do as we work through this quarter and tackle different types of functions are to also try and tackle getting familiar with some of the really classic calculus applications you're going to see as you continue. So we won't be able to entirely solve these problems by hand. Part of that work will happen in calculus, but we can absolutely tackle the setup and we can finish these off using technology, or we can just stick with the setup part of it, and this is going to help so much when you get to calculus. Otherwise, this can be a really challenging piece of a calculus course. So one of the classics is like the barn fence problem. I've given you a little bit of a variation on that. It's fencing a garden. But the idea is you're trying to enclose some sort of rectangle and you have a fixed piece of information about your perimeter, or sometimes it's vice versa. So in this situation, I'm trying to fence a garden, and one side of this garden is going to sit against a stone retaining wall. So we don't actually have to enclose that with the fence. We just have to capture the other three sides. So we don't know exactly what this rectangle looks like. That's part of our job in this problem, is to figure out the dimensions of this rectangle, but we do know it's a rectangle. We do know that the three sides have to be enclosed with 80 feet of fencing. And we do know that we're trying to make the largest possible garden. So when I say largest possible, I'm going to interpret that as maximize area. I want the maximum possible area. Okay, so a picture is always a really good idea in these problems. Another very nice first step is identifying that we need to maximize area. Tells me right away what my formula, what my function needs to represent. I need an area function. So let's say A is the area of the garden. So we're writing a formula for area. And I really encourage you, unless you're super quick at these and you don't have to think very hard about it, to try and break this down a little for yourself. When I say I need to maximize the area of this garden, one thing that jumps out at me is it's a rectangle, and rectangles are actually fairly simple to find the area of. So I know that the general structure of this needs to be length times width. And you can use L and W right out the gate if you'd like to. I find that sometimes in these problems, students get lots of variables going and they get tangled. So I've been trying to get in the habit of writing some of this out with words until I decide what variables I want to use. But you certainly wouldn't be in trouble for writing A equals L times W here. Okay, let's go for it. We need a variable, preferably only one, but I think we might need two at first, that tells us, that represents dimensions, that somehow will help us get the length and width of this. So for this one, let's just go ahead and say I'm going to call one side X and one side Y. Again, you can use L and W if you want, but I want to kind of set this up with different variables so you can see how it becomes a fill in the blanks, and just writing in words length and width kind of helps keep the confusion down a little about what goes where. So my problem is, to represent dimensions, I need two variables. And my goal here is to have two variables total. So A and one other variable. Right now I have A and two other variables. The idea being, if I have A and one other variable, that's like an X variable and a Y variable, and I know how to graph that in two dimensions and look for maximums. I might need technology to help me with that unless it's a quadratic, but I do know how to look for maximums. So I need to figure out how to boil this down to a single one of X and Y, not both, but just one of them. And you'll hit a point like this in a lot of these sorts of problems where you need to go looking around for the extra piece of information that keeps you from having free choice. So the question here is, why can't I just say the length is 10 and the width is 5? And the answer is because of this 80 feet of fence. If we're going to maximize area, we most definitely want to use all of the fencing. So using a 10-foot length and a 5-foot width, that's very silly. We don't get even close to using up the 80 feet of fence, and we won't get even close to finding the biggest possible garden. So we want to write basically a perimeter formula. So with the way that I've labeled this, my fence has to cover the y dimension coming down, the x dimension going across, and then the y dimension going back up. So I need to cover an x and 2 y's with my 80 feet of fence. So maybe not quite perimeter because we don't do the third side, but definitely related to that idea of perimeter. So it's my fencing formula. And this is not going to become my new equation. My equation is absolutely still the area equation. I need to maximize area, so I have to have an area equation. The idea here is that I can now write that area formula with only one variable. So if I say that x is the length, then I can use this formula to replace y with something involving x's. So back over here, I could subtract x from both sides, and I could divide both sides by 2, and I will get y equals 40 minus 1/2 x, or x over 2. You could also leave that as one big fraction. 80 minus x all over 2 would be okay, but I think splitting it up is maybe a little easier to deal with. So back over here, I can say I'm calling y the width. The width is 40 minus 1/2 of x, and that has to be true for us to be using up our full 80 feet of fencing. So that's what turns this into one equation with two variables. And from here, we should be able to find a maximum. And in fact, since it's quadratic, the maximum should be the vertex. So I actually think I really like this factored form, but just to point it out here, if we did distribute, we'd get 40 minus 1/2 x squared. That negative in front of the x squared says this is a parabola that opens down, so it will have a maximum. There are multiple ways to find that vertex, that maximum. My favorite way, if you can get something factored, which this is factored already, is to find its x-intercepts and then say, well, the vertex has to be right in the middle. So as my side work to find the max, I would say, it seems maybe a little counterintuitive at first, but I would set it equal to 0. And the point here is that you don't really have to do any work, so I'm writing this out just to make sure everybody follows. But the idea is you would set each factor equal to 0. So x equals 0 means it crosses at 0, 0. And then 40 minus 1/2 x equals 0. If you solve that, you should get x equals 80. 40 minus half of 80 is 0. Which means it also crosses at x equals 80, and we already know it should be doing something like this. And parabolas are perfectly symmetric across this line through their vertex, which means that vertex has to be exactly halfway between 0 and 80. In this case, I don't even need to do the arithmetic. If the numbers are messier, you could add up your two x-intercepts and divide them by 2. But here I can just spot it, that the max happens when x equals 40. So we get a max area if x is 40 feet, and then we can refer back over here and say we need the other dimension as well. The question was, what are the dimensions? So y is going to be 40 minus half of 40. Plug your x value in. And y is 40 minus 1/2 of 40. So 40 minus 20 is 20. Y equals 20 feet. So if we choose a length of 40 feet and a width of 20 feet, we will have the maximum possible area for this rectangle. There are variations on this, but this is kind of the basic structure of some of these fencing problems. Thanks for watching.